Good afternoon, everyone. My name is Sheila McIlraith. I'm a professor in the Computer Science Department here at the University of Toronto, a Canada CIFAR AI Chair at the Vector Institute, and also an Associate Director and Research Lead at the Schwartz-Reisman Institute for Technology and Society, SRI. I'm delighted to moderate today's SRI seminar featuring guest speaker Jeff Clune. I'm also pleased to welcome you to the first SRI seminar series of the fall 2025 semester. We hope you'll find this series to be a welcoming and inspiring place to learn about important research at the intersection of technology and society, and also to discuss the societal implications, benefits, and challenges of AI systems and data-driven technology. We really have an excellent slate of speakers lined up for this semester, so I hope this won't be the only seminar that you attend. Before we begin today's session, I'd like to take a moment to acknowledge the land on which the University of Toronto operates. For thousands of years, Toronto has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and we're very grateful to have the opportunity to live and to work on this land. While some of you are joining from different places today, we invite you also to reflect on the history and relations of the land that you are on. Before we begin, just a few logistics. This session is being recorded. Jeff will speak for about 50 minutes and will be followed by a Q&A. We were chatting before we started, went live, and Jeff said, since we have a fairly long period for the Q&A, most people if you can wait to ask your question, please do so. But otherwise, if you're not going to understand the rest of the talk because you need some quick clarification, then raise your hand and we'll try to watch and let you ask that clarifying question. During the Q&A, we'll encourage participants to engage by using the raise hand function in the Zoom meeting controls or to type questions in the chat. So I'd just like to introduce Jeff, who is a professor in the Computer Science Department at the University of British Columbia. He's a Canada CIFAR AI Chair at the Vector Institute, and he's also a Senior Research Advisor at Google DeepMind. His research focuses on deep learning, but particularly on deep reinforcement learning. Before Jeff took on these last positions, he served as a Senior Research Manager at OpenAI and was also a founding member of Uber AI Labs, as well as holding positions at University of Wyoming and Cornell prior to joining UBC. Jeff has received numerous accolades. He's received the Presidential Early Career Award, which is a very prestigious award, as well as an NSF Career Award while he was in the United States. His work is featured in leading machine learning conferences and journals, as well as notably publications in Nature, in Science, and in the Proceedings of the National Academy of Science, which are really some of the preeminent venues for work of this nature. He's also received a number of honors, too many to list, but I will highlight an Outstanding Paper of the Decade Award, which is quite something, Distinguished Young Investigator Award, as well as a number of Test of Time Awards, which are particularly notable because they really are retrospective awards for work that has been highly impactful. So without further ado, please join me in welcoming Jeff, whose presentation is entitled Open-ended and AI generating algorithms in the era of foundation models. Jeff, over to you.
Hello, everyone. Thank you very much, Sheila, for the wonderful introduction. And it's great to be here. I'm a huge fan of SRI, so it's great to talk to you today. Fun fact that I was reminded by Sheila's introduction, my daughter's name is Seneca, in part because my wife and I got engaged on the shores of Lake Seneca, which is not too far from where you are. And for many other reasons, Seneca Falls being the first women's rights conference, and Seneca, the philosopher, actually two of them, the founder of the Stoic school. So anyway, that's some fun background for me. I am delighted to talk to you. I'm going to share my slides here. Where did my presentation go? It disappeared. That's strange. No, it's not there. Here, let me try to get out of presentation mode and then try again. Sorry, we rehearsed this so much that I think we got it into a state that it doesn't want to succeed from. Here we go. All right, sharing full screen. Can somebody confirm that you can see my screen?
Looks good.
And can you tell me, can you see my mouse, Sheila?
Yep.
Perfect. All right, let's do it. So Sheila read the title of my talk, so I won't say that. So today, my goal is to kind of introduce some algorithms that you may not be familiar with, unless you've heard a talk by me before or some of my colleagues. These are quality diversity algorithms, open-ended algorithms, and AI generating algorithms. And then I want to spend, after I kind of motivate those algorithms and introduce them, I want to talk about like new opportunities that have been unlocked by what I'm going to call foundation models, but you might call LLMs, frontier models, pre-training, GPT, etc. So I want to start with an observation, which is a paradox, which is that if you try too hard to solve a problem, you will fail. If you ignore the objective altogether, you're much more likely to succeed. Now, this only is true for extremely hard problems, like getting to the moon or time travel or something like that. So if you, as a metaphor for that, imagine that you're an agent and you start in the bottom of this maze here, and you only reward yourself for going closer to the goal. Well, here's an algorithm that did that. And what you get is most of the agents go north and bounce their head against this wall forever. Because there's a deceptive local optima here. If instead you completely ignore the goal, you don't try to get closer to the goal, and you just explore, well, then you trivially explore the maze and solve this problem. Now, you might say that is a kind of a toy problem, but in fact, this happens all the time in the hardest problems we try to take on as a society. So, for example, in the history of science and technology, this is a routine occurrence. Imagine you went back thousands of years to cooking technology like this, and you said, I will only reward and fund scientists in my queendom that give me more cooking faster for less smoke. Well, then you would never invent the modern microwave. Because to invent the microwave, you had to have been working on radar technology and noticed that a chocolate bar melted in your pocket. Similarly, if you went back to the time of the abacus and you said, I will only fund scientists to give me more compute per second, you would never get the modern laptop, because to invent that, you had to have been working on vacuum tubes and electricity, which were not invented because they help in terms of computation. So if you try to solve the problem directly, you will fail. So the conjecture here is that the only way to solve hard problems may be by creating problems while you solve them and goal switching between them. So goal switching is this idea that we had in 2016, which is if you're trying to solve one task, like a roboticist trying to get bipedal locomotion, and you make progress on a different task, such as balancing on one leg or crawling on all fours, don't throw that out because it doesn't measurably improve your current objective function, which is forward speed. Instead, you might say, that's an interesting new thing to be practicing. Let's start working on that also, and simultaneously work on crawling and maybe balancing on one leg and trying to walk forward. And that will end up allowing you to capture serendipitous discoveries. Like you're in a lab, something interesting and weird and cool happens, start investigating that as well. That's what we want our algorithms to do. And that leads us to this family of algorithms that my colleagues and I have been creating called quality diversity algorithms. The idea here is that you don't try to get a single best solution in a search space. Instead, you try to produce a diverse set of extremely high performing things. Just like all of the creatures that nature produced, visualized here, are all wildly different, but are extremely good at the weird thing that they do in the world. So that leads us to this algorithm map elites. This is basically the most popular quality diversity algorithm, I think by a couple of orders of magnitude. My friend and I co-invented it in 2015, Jean-Baptiste Moret. And the reason I want to walk you through this algorithm is because the same basic playbook is going to be used over and over again for the next 10 years of my career and in many of the papers you're going to see in this talk. So it's pretty simple, actually. Imagine that you are trying to optimize for a robot body, okay? So you're going to pick dimensions of variation you care about. Here it's height and weight. And then you pick some performance measure you care about, like forward speed. And then what we're going to try to do is we're going to try to create a multi-dimensional, so here are two-dimensional, archive of phenotypic elites, phenotype being an evolutionary term for like the characteristics of the thing. Okay? And so the idea, after we've picked these dimensions of variation, we parameterize an agent with some parameter vector like theta, evaluate it, figure out its performance, which is colored here in blue, and then its properties, its height and weight in this case. and we'll just put it into that cell on the map. And then we run this loop. We take something out of the map, we change it a little bit, we reevaluate it, we figure out where it goes in the map. And if it's the best thing we've ever seen at that location in the map, swap it in. That's the elites part. Okay, so what's cool about this algorithm is instead of giving you one best solution that I found, it gives you a set of solutions, each of which is the highest quality thing we found for that type of thing. And you can do a lot of stuff with a set of high quality, diverse solutions, as we will see. For example, at Cornell, I had been working on this problem, this soft robots problem, and I got this parade of creatures here that are all interestingly different. But there's a trick to this video, which went viral at the time, which is that every one of these solutions came from a separate run of optimization. Within that run, it had basically figured out that one thing and had minor little changes to it. So I was only getting diversity through restarts, but that's not what we want. We want to be able to run one algorithm, one run, and have it produce a diverse, high quality set. So I tried that. I tried Map Elites once we invented it on that problem. And as a control, we did classic optimization. So if you just run search in this search space, no diversity, you get low performing creatures here. They're all black. They don't run very fast. If you explicitly reward for diversity in some multi-objective algorithm, including diversity in these two traits, you don't get that much diversity. It doesn't search the search space very well. It does improve performance, so diversity does help, but it doesn't search the space very much. With the exact same number of evaluations, so the same compute, this is what Map Elites gives you, which is just a complete sea change in terms of what an algorithm does in exploration and figuring out what's going on in a search space. So you learn that there are multiple different optima here, and you learn that you can't do very well in these parts of the search space, etc. Another important thing is we can do science on these algorithms and study the extent to which goal switching is critical, and it turns out it's essential. So if you take a starting organism like right here, and and you go through the history of like the lineage that leads to a final best point. So here's the final best thing we found. What is the path through the search space that its ancestors took? What you find is it didn't just optimize for one type of thing. Instead, it traversed this long circuitous route through the search space to ultimately produce that extremely high performing thing. Just like you might not know it, but your ancestor was a flatworm. So for whatever reason, to get bilateral symmetry, you had to go through the flatworm stage. And if anyone was trying to evolve the most intelligent thing on Earth, they probably wouldn't have been incentivizing a flatworm. So these algorithms create their own counterintuitive curricula through the search space that ultimately prove to be essential. So we used these ideas in 2015 in this paper we had in Nature. You can actually see the Map Elites grid on the floor there in the article. And the idea here is we're going to get in simulation ahead of time as many diverse, high quality ways to walk with this robot as possible. And then once it becomes damaged, we'll quickly use Bayesian optimization to find a gate that works despite the damage. That allowed us to adapt in about 6 experiments, 6 to 12, and about 1 minute of real clock time. Another use of this same basic playbook is in this algorithm that you might have heard about called Go Explore. So the idea in Go Explore is that at the time and still, hard exploration problems are basically bedeviling reinforcement learning. We don't know how to work in challenges, in optimization problems, in environments where we very infrequently get reward, and we have to figure out what to do. So at the time, this problem, which had become like a grand challenge in the field, was called Montezuma's Revenge. That was like the exemplar problem of hard exploration because nobody was making any problem on it. And in this game, you have to take all these actions before you get any reward. And so it was a real good challenge for the field to try to figure out what do we do when we're not getting signal reliably. So the idea of Go Explore, or one of the main ideas, is that we want to learn the highest quality way to get to as many different states as possible. So that's quality and diversity. And there's some extra stuff that makes that happen. But once you do that, you basically blow the roof off of this problem. So all of these blue dots here are papers that had, set the state of the art on many other Atari games, which was the main benchmark at the time, but made almost no progress on Montezuma's Revenge, even though some of these papers specifically target Montezuma's Revenge and didn't make much progress. In contrast, Go Explore just basically went, blew the doors off, or the roof, Ended up beating the human world record on this game, which was pretty impressive. And then we went on to test Go Explore on all of the other problems in the Atari suite, and it basically exceeded state-of-the-art or human performance on all of the games, and effectively was the first thing that beat this benchmark, with some caveats you can see in the paper. It also solves really hard, sparse reward problems in robotics. So here, this robot struggles in the same way my children do, which is to put away their toys. Here, we're only going to reward the robot if it puts away a toy successfully. And what you can see is that even intrinsically motivated PPO gets 0 reward, that's orange, and Go Explore solves all 4 of these problems. So quality diversity algorithms, I hope you agree, are pretty interesting. They produce a diverse set of high-quality agents. They do exploration via goal switching and inventing these counterintuitive curricula. So what's missing? And the answer is they're still stuck in a single environment. So traditionally in ML, we pick an environment like Go or StarCraft or Dota, and we work on it really hard. We make algorithms that do pretty well. We scale the heck out of those algorithms until we do really well on that problem. And then we, the human scientists, say, okay, now I'm moving on to the next problem. But that's not what we want. My friends and I, for decades now, have been trying to create these things called open-ended algorithms. And the idea here is that we want to create an algorithm that endlessly innovates. I mean, really, truly endlessly innovates. The longer you run it, the more it invents, is creative, innovates, learns, comes up with new stuff forever. And so an example of such an algorithm is natural evolution. If you look to the right here, it produced all that crazy stuff, including jaguars and hawks and the human mind, and it's still going, right? It surprised us with COVID. It surprises us all the time. Another, and the only other example of an open-ended algorithm that we are aware of in the universe is human culture, right? Science doesn't end. Every time you solve a new scientific problem, it unlocks new questions. Every time you invent a new technology, it allows you to ask and try and do new things. And so as we go, solving problems creates more opportunities, more learning challenges, more problems, if you want, forever. So one way to frame this is, could we make an algorithm in a computer that was worth running for 1 billion years? Evolution has been running for 3.5 billion years, and it's still going. Could we create a computer algorithm that would be worth coming back and checking if you gave it 1 billion years of compute and a planet-sized computer? So that is the grand challenge, if you will, of open-ended algorithms. So one of the things I think is probably the key ingredient to open-ended algorithms, as I mentioned, is that every time they solve a problem, that unlocks new problems, new opportunities. Just like leaves high up in trees were a solution to get sunlight, and that created the opportunity or the problem that then giraffes and caterpillars can solve by eating those leaves. And then giraffes and caterpillars are new opportunities for things to eat them, cooperate with them, live inside them, etc. So an algorithm we put out in 2019 that was trying to push in this direction was called the Paired Open-Ended Trailblazer, or POET. And the idea behind this algorithm is it's going to endlessly generate increasingly complex solutions and diverse learning environments forever. That's the idea. And this is one of the first papers that really started the now very modern trend of automatically generating environments to train agents in. So in POET, we're going to encode the environment itself with a parameter vector. We're going to periodically generate new environments, and then we're going to follow that same playbook from McIlraith. So we have an archive of environments. We pull one out, we change it in some way. If it's not too easy and not too hard for the current set of agents, we'll throw it back in the archive, and then we'll allow goal switching. So agents from one environment can then switch into that environment if they're the best thing we have for that environment. And just like a squirrel can invade a new niche, then these agents can kind of invade a new niche, which is an environment that's been creating. So we're going to allow goal switching to happen. You could also train a generalist agent across all environments, and it kind of implicitly allows goal switching. As it learns new skills, it can try new things in different environments. So here, every environment you see here was automatically created by the system. It starts out by having simple challenges, little tiny stumps, little tiny gaps, a little bit of rugged terrain. And as it goes, it's inventing its own curricula. So eventually it starts to say, I can put together bigger stumps, bigger gaps. And eventually it kind of basically pushes the limits of what's possible with this little two-dimensional physics body. One thing I love about digital evolution is it's much easier to do science. So here we could kind of test out to the extent to which goal switching was important and the curriculum was important. So we take all of these environments that the system created and solved. We can go back and try to directly optimize with the same learning algorithm. Can we solve that obstacle course? And the answer in every single situation is no. So without a curriculum, you can't go anywhere. Now you might think that's not fair. You need a curriculum. So we tried to create a direct path curriculum to each of these challenges, and in every case that failed as well. We needed these weird counterintuitive curricula invented by the system, just like vacuum tubes and electricity. So a later version, an enhanced version of Poet had a more complicated environment search space and some other tricks. But I want you to just see all of the diversity that you're seeing here is all popping out of one run of this algorithm. So much diversity that you're getting. It's really interesting. And maybe this algorithm would be interesting to run for a very, very long time with lots of compute. We didn't have the compute to see its limit. This right here is one of my favorite plots of my entire academic career. This is a phylogenetic tree of environments created by the system. And what you can see is that the search is really healthy. Like evolution, it produces totally different styles of solutions. In evolution, it might be like the big cats or the big dogs or aquatic creatures or insects. And then once it creates that idea, it riffs on it, expands on it, and just mines that gold, that vein of gold for a really long time. So you get these deep phylogenetic branches, which suggest sustained exploration in different directions, which you'll have to take my word for it. Like myself, I spent like 10 years trying to produce a plot that looked like this and failed. And this was the first time I ever saw it, which is pretty cool. People took Poet and they basically added a couple more tricks and got it to train robots in simulation that you could then transfer to reality. And it was just really cool to see these ideas produce such like science fiction level robots. At the time, it was like crazy to see robots out in the real world solving these sorts of problems. It's becoming more routine now. So to conclude the Poet part of the talk, it shows the benefits of quality diversity and generating challenges while you are trying to solve them. So what's missing? And the answer is we're still kind of stuck in this single narrow distribution of environments. We want to break out of that wildly. So I want to take a step back for a second and talk about the biggest ambitions of our field. So if you agree that we should make AGI, then I think we still have a long way to go, although this slide's becoming a little dated as we make progress. But I think that begs the question still of how will we get all the way to the final milestone? And I think there's a clear trend in machine learning, which is that hand-designed pipelines give way to learned pipelines as you have more compute and more data. So just learn everything is the answer. We've seen that with features, architectures, hyperparameters, data augmentation, even the RL algorithms themselves. When we get out of the way and stop trying to be clever, you get the better lesson and things start to work. So that suggests an alternate path, which I call an AI generating algorithms paradigm. The idea here is we're going to do lots of pre-training, lots of search, lots of compute to ultimately produce some agent, and that agent will be extremely sample efficient at learning. And we have an existence proof of that. On Earth, we took a planet-sized computer and an open-ended algorithm, did a lot of search, and ultimately produced you. Congratulations. You're the smartest thing we know of in the entire universe. So this is possible, and I think we could create computer algorithms that do that. So I think if we want to make progress on this, we need to simultaneously push on three pillars. We need to meta learn the architectures, which, by the way, is a field that has not yet beat the transformer, so more work needed there. We need to meta learn the learning algorithms themselves, and we need to automatically generate effective learning environments. Now, so far, well, actually, just to point out, all three of these are things where we could try to use our brains, or we could try to unleash machine learning algorithms and compute. And the AIGA philosophy is that the machine learning, learn it all, let the computer do all the heavy lifting. That is going to win in the end. And so I think we should just embrace it and go for it. Now, so far in this talk, I've been focused on pillar 3, automatically generating the learning algorithms. And we'll spend some more time on 3 and 2. So, okay, so far in this talk, I've now teed up what is a QD algorithm, what is an open-ended algorithm, and what is an AI generating algorithm. And so for the rest of the talk, what I want to do is talk about kind of our modern work in this, which is to say, how do these algorithms, which I've been working on for 10, 15 years now, how do they get unlocked now that we have foundation models? So that's what we will spend the talk on. The first piece of work I want to tell you about came out of my lab here at UBC, led by the great Jenny Zhang, who may be on the call, and with excellent collaborators, Joel and Ken, who have been on this open-endedness journey with me for a very long time. And so the idea here is that to produce open-ended algorithms and AIGAs, we need a vast environment task search space. So how are we going to do that? Well, the problem is, if you have a truly vast search space, you now have a needle in a haystack problem, because every new problem that you want to spend compute on has to be both learnable and interestingly new. But most of the tasks in your search space are impossible, nonsensical, too hard, too easy, or just boring. They're not worth spending time on. So how are we going to find those needles in the haystack? Well, for learning progress, we have some pretty good methods. In fact, my team at OpenAI put out a paper that worked really well in terms of measuring learning progress to create a curriculum. We did that in Minecraft. So we're going to basically just use that idea. The real problem, the real challenge is, how do you define this thing called interesting and interestingly new? So to motivate that, you should recognize it's really easy to have learning progress without it being interesting learning. For example, if I just generate a random number, 1 trillion digits long, and I go to an agent and I say, memorize the first 3 digits, now the first 13, now the first 23, and I'm always giving it 10 more digits to learn, well, there's infinite learning progress. There's always something to be learned, but that's completely useless. Why would we want to do that? So the problem is, for like 20 years or more in the field of A-life and open-endedness, we've been trying to hard code, and in RL, what counts as like a good intrinsic motivation for an agent to go do something interestingly new. And whenever you try to code up what you think should be a good measure of the robot doing something interestingly new, or the agent, and then you optimize against that function, you always get pathologies. It never works. For example, you say to a robot, go find new states, and it just sits down in front of a TV tuned to a dead channel, and it gets an infinite amount of states there. Or you tell a robot, do a new body configuration. Fine, it just twitches randomly its muscles forever on the ground. So this kind of relates to this famous quote from Justice Potter Stewart, which is, there are things in the world that we don't know how to define, but we know them when we see them. And so for my whole career, we have not had an answer to this until we realized recently, wait a second, foundation models can serve as the answer here. They have read the entire internet, including lots of people on Reddit describing what they consider to be boring, and a few people admitting that they find something interesting. They've distilled this ineffable concept of what it means to be interesting into the weights of billion parameter models, and we can just ask them, hey, I'm already good at these 10 tasks. What's the next interesting thing I should work on? And so that leads us to Omni, which stands for Open-endedness via models of human notions of interestingness, where a foundation model pre-trained on the internet is going to be our model of human notions of interestingness. So what we're going to do in Omni is we're going to generate tasks for an agent. We want them to have high learning progress. We use the work from my team at OpenAI. And then we're going to just ask a foundation model, hey, we just got this task proposed to us. It has high learning progress, but is it interesting given what we already know how to do? And we'll use that to filter things out. So if we tried this in these 2 domains here, Crafter and Baby AI, if you do uniform sampling of tasks in this space, that's the red line, you get no performance, nothing works. If you do learning progress only, it works better, a lot better. That's blue. But if you then also filter on whether or not the task is interesting, you make a more efficient use of your training, and so you learn more tasks. Now, how are we measuring performance here? What's on the y-axis? Before we started training, we defined a set of tasks we think would be good for the agent to learn in this task. Actually, we didn't do it. The people who created these domains did. And then we say, hey, we're just going to unleash an open-ended process that is not trying to solve those tasks. It's just trying to learn interesting, diverse tasks. But we can measure it against those held out tasks and find that it works really well. Now, We're still in those problems. We were still in a set of small handcrafted domains, handcrafted tasks. We wanted to really go for a bigger search space. So we said, let's take a complicated simulated world like this kitchen, and then we're going to have a truly infinite task space, which is the space of all possible tasks you could describe in natural language. The problem is once you can ask for any task, like put the salt inside of the toaster and put that under the, in the sink, you then need what we call a universal reward function, which is a reward function that will tell you if you have accomplished any task you could ask for. And that stymied us for a little while. We tried video models, like showing a video to a video language model. Ultimately, I think that's the right answer, but that didn't work because they're not good enough yet. So what we ended up with is just saying, oh, we can ask a foundation model for code, a reward for code for the reward function. So now we have the GPT spit out the reward function as well. It gets to query the state of the simulator to find out if a thing has been done. So in this much bigger search space, uniform search doesn't work. Now learning progress also doesn't work. There's just too many tasks that have high learning progress that are boring and not worthwhile. Whereas if you let Omni drive, then you get much better sustained learning over time. What's also cool is it creates these really nice curricula. So first it says, go get an apple, then go figure out how to find and pick up a knife. And then later on, it's like, oh, let's see if we can cut an apple with the knife, and on and on and on and on. All right, so I think Omni is super interesting. It allows us to get an infinite task space, but we're still in that kitchen. And I don't want an algorithm that's trapped in one kitchen or one office building or whatever. I want the whole enchilada. So we need is a truly vast environmental search space. That's the goal of open-endedness. So that leads us to this idea that I put out in my 2019 AI generating algorithms paper, which was, I was trying to think at the time as I was writing that paper, like what would be the richest search space imaginable? And I said, well, we want something that basically has enough diversity that it could simulate all of the kind of environments you see on the natural world where Darwinian evolution reigns. And I said, well, what if you had the idea of a search space that could be and contain any computable environment, anything you can think of, logic problems, math problems, fluid dynamics simulators, forests, whatever, that's in there. So I call that a Darwin complete search space as a nod to being Turing complete. And I put that out as like a theoretical thing that should strive for. And at the time, I could only think of one search space that would fit that bill. I'll return to that later. But recently, based on a comment of one of my students in my class here at UBC, I realized there's another one, and that's code. So code is Turing complete. If a system can code up the environments in code, like Python, then it's Darwin complete. So that leads us to this paper called Omni Epic, which we're just going to do Omni. But now, rather than being in a simulated kitchen, we're going to also let the system generate the environment writing code so it can create any sort of environment that it wants. This is again was done with Jenny and Maxence and Antoine Coley. So I said all this. Omni is going to produce code for the environment and for the reward function and is thus Darwin complete. And here are like the results in visual. So we start with one seed environment, and then every environment you see here was automatically generated by the system. And there's a curriculum. So first it starts with this robot that can go across these platforms that move up and down. Then it goes, I'm skipping over some, but then it goes and creates like kicking a ball through goalposts. Then it makes like the platform separated, the obstacle course, and it creates an obstacle course. It eventually says, let's knock over some dominoes, let's knock over a stack of blocks, etc. And so we didn't have enough compute to run this algorithm because learning each of these environments is very expensive. So we wanted to simulate what would happen if we let this thing really go. So here we're going to pretend that the agent can solve every environment that gets generated and see what happens. And what you get is another kind of phylogenetic tree. It invents different classes of environments. And then it kind of continues to make them harder and more interestingly different. So you get environments like searching a building, like running up a ramp. You get like kickballs through goalposts, kickballs off a wall through a goalpost. Eventually it's kick a ball through a moving goalpost, and then kick a ball through a moving goalpost with moving obstacles. Some of my favorites ended up being it created a construction site to clean up, and then a restaurant with cluttered tables that the robot waiter has to clear take to the kitchen, and on and on and on. Yet again, this is an algorithm we might want to run for a really long time, especially if we had a learning agent in it, and see what happens. So to conclude this like Omni mini chapter of the talk, we have the ability to finally focus on interesting tasks because foundation models have learned that ineffable concept from humans. So we no longer have that Achilles heel. We also now can generate any possible environment that you can put in a computer. So we're pairing the idea of interestingness, interesting open-endedness, or open-endedness that focuses on interestingly diverse problems with a Darwin complete search space. So this is one of the first algorithms in my entire career that I might want to run for 1 billion years and see what happens. I'm sure it would break down and then we'd have to patch it when it does, but it's starting to feel like we've got some candidate algorithms that really deserve huge amounts of compute. So, as I mentioned, when I first came up with Darwin, the idea of being Darwin complete, I had an idea for it. And I almost didn't put it in my 2019 paper because it seemed so crazy and so wildly futuristic that I thought it was a career risk to let people hear that I thought this would ever be possible. I thought they would just dismiss me as kind of like a crackpot. And the idea was, what if you had a neural net that was the entire environment? It is the video game, it is the simulator, whatever. It generates a full high resolution image of like a video game, and then you give it an action, and it is the transition function. It steps to the next state of the world. The agent sees that output, and it takes an action, and then you step. And it could do an image, it could do sound, smell, touch, whatever the agent can sense. It is the entire universe. And I was like, I don't see any reason in principle why a deep neural net can't do that. But I want to remind you, in 2019, that was like crazy talk. That's like laugh a person outside of the room for ever proposing that. And here we are, 5 years later, 4 years later, and the Genie project comes out of DeepMind. So my colleagues and I, led by the people you see up here with asterisks, worked on this thing called Genie, which is exactly that idea. It is a neural net that is a world model, and it can generate any environment you want. So you ask it, condition it on text or image or a sketch or whatever, it will give you an initial frame, like a picture of a world. You give it an action, it gives you the next frame. You give it an action, it gives you the next frame. Or the agent gives an action and it gives the next frame. And we just train this thing from online videos at massive scale, and really good things happen. So here you say, I want to create a world with a little orange clay creature that I can run around in a 2D platform world. It generates this initial picture. You give this picture to Genie and an action, and you can start making that little creature jump around. And here you can see a lot of different games that Genie invented in its own mind. This is all just in the mind of a neural net serving as the world. So it was so crazy to see 4 or 5 years later, this thing that I almost was afraid to admit publicly I thought might be true and possible, turn into an actual research project. But at the time I put on Twitter, remember, this is the worst it will ever be. It will get better. So hold that thought. So what was also fun is in the blog post, we decided to see whether or not children can draw a world and then step into that world that they have created. So we took art from my kids who were then 7 and 9. There's Seneca, I mentioned her name earlier. And my kids made these drawings, and then they could make them move. They could control the creatures they made. They could step into those worlds, which is pretty crazy. You can do it for robotics, train on robotics videos and have a robotics simulator, etc. So this is basically a foundation model, but that's a foundation world model. And like foundation models like GPT, they're general. You can build on top of them. You can fine tune them with supervised fine tuning. You can do RLHF. Scaling laws apply, etc., etc. So there's lots of analogies to generative models here. And we did some studies on scaling laws. More compute, more data, more better. So that leads us to Genie 2. I think this is only like 9 months later. Look how much better this is. Now you can hit buttons, you can walk into a ship. It's no longer a 2-dimensional platform game, it's a 3-dimensional world. You can walk around in this thing, and you could imagine how cool it would be to train an agent in this massive diverse set of worlds that Genie 2 allows you to create. But when I put this on Twitter, I was like, remember, this is the worst it's ever going to be. Scaling laws still apply. And so in the future, it's going to be even better. Here's an example of a world in which you can see Genie allows you to train and go and make different choices. So you could go through this left door and investigate that world, which is some cool phosphorescent avatar world. You can go into the middle here, some sort of tunnely thing, or you could go up the stairs. And so these are real world models that allow you to explore different things and learn different things inside of them. You have fine-grained control. You have even object interactions. So you can blow up this thing here on the left. You can go take your samurai sword and chop balloons, which sounds like a really fun video game, etc. Now, a couple of months ago, you might have seen it. I think this is about maybe 3 weeks ago. Genie 3 comes out. So we just scaled it up. Actually, I'm not a part of this project. This is much more of like an engineering scaling move. And so here is now a really high-res world where if you wanted to train to fly a helicopter, maybe you can do that. Or maybe you want to like have fun as an agent learning how to drive a jet ski around and bonk into lanterns on some beautiful lake, wherever this is. Or you want to control a firefly to explore a world where there are tree houses. So both for human entertainment and making video games, but also for open-ended agent training, we now have a second Darwin complete search space, which is starting to get really good, that we could unleash our open-ended algorithms in. Here's another fun one. My kids love this one. All right, we won't go through all these examples. So as I said, when Genie 1 came out and Genie 2 came out and now Genie 3, I'm going to say the same thing. This is the worst it will ever be. It will get better. Imagine open-ended algorithms like Omni paired with Genie 4 or Genie 10. This is an extremely powerful opportunity for open-ended learning. All right, so we've spent a lot of time on pillar 3 here. We've got QD algorithms, open-ended algorithms, including Poet, Omni, and Omni Epic, Parry and Genie. All of this is Darwin complete search spaces now, so we're really making a lot of progress. I want to switch to pillar 2 for a little bit. Pillar 1 I'm going to leave alone. That's a whole separate field that I've not been active in lately. We'll see if there are major breakthroughs. I predict that there will be. But anyway, pillar 2, we want to meta-learn the learning algorithm itself. Well, one of the problems that I thought about when I got to OpenAI and I was figuring out what we wanted to work on is that if I can create these open-ended algorithms, I can generate environments forever like Poet and Genie and Omni Epic, there's still another problem, which is that training the RL agent to solve the next problem and the next problem and the next problem is really sample inefficient. And so at this point, the problem is no longer can we generate interesting, diverse environments. The problem is it takes so long to learn each successive environment that we don't get to see the algorithm really go for very long. And so RL often fails to learn because exploration is too hard. And that really is now a tax on open-ended algorithms and seeing what they can do. So a question that Josh Tenenbaum asked me at iClear in front of the whole conference, put me on the spot, was, can we make AIGAs without a planet-sized computer? And I think the answer is yes. And to borrow from Newton, I think that AI sees further by standing on the shoulders of giant human data sets. And so what does that really mean in practice? Well, we can go to the internet and have our agents train on all the data on the internet. Just like GPT is really good out of the box at solving like writing problems, we can have embodied agents watch all of the videos of agents doing things like humans playing Minecraft or humans, doing gymnastics, and they can learn how to act. So we decided to test this in Minecraft. We said, hey, let's go get a bunch of videos from online and let's pre-train on them to know what we should do in every situation. A challenge is that videos don't come labeled with actions. So if you're trying to generate text, music, or images, you get the next word, the next pixel, the next note for free in your data. But if you're trying to say, what action should I take at every moment in this video I'm watching of somebody playing Minecraft, you don't know if they hit jump or left or up or what makes some crazy keystroke combination. So we need the action at every time step. Well, we realized that there's actually a pretty easy solution to that. If we have some videos, a small set of videos where we have action labels, then I can train a model that looks at the past and gets to see the future. And all it has to do is a pretty easy task of saying what action must have been taken at that transition. For example, if you see these two frames, you know that the character must have hit the jump button here. So once you train the inverse dynamics model, which is a big neural net trained on labeled data, to predict an action for every transition, now I can use that IDM to go label the entire internet's worth of videos. We took 8 years and 70,000 hours of Minecraft video, and we trained a 500 million parameter model to basically predict, given the history of actions in video, what is the action that a human would take in this situation, in this situation, in this situation, and you get an autoregressive model that you can roll out in the simulator. What we found, as is no longer will surprise anybody, is that scaling laws work. So the more data you give it, the more skills you start seeing zero shot out of the box. And then if you do some supervised fine tuning, you get some really impressive behaviors. I want to call your attention to this video on the right. You drop this pre-trained agent in a village in Minecraft, it knows how to explore. It goes from one room to the next room. It knows if it sees a chest, it should open it. If it sees a door, it should open it. It doesn't just randomly mash its buttons and twitch forever and hoping something good eventually happens. It has learned systematically how to see the world, explore the world, act in the world, and go seek what the world wants it to do, like where the rewards might be. So if you have this sort of an agent and you drop it in an open-ended algorithm, you're shaving off orders of magnitude in terms of your sample inefficiency. So to show that, we wanted to say, hey, can we accomplish what was then a grand challenge in Minecraft, which was trying to get to an agent that could get from the starting state all the way to a diamond tool. This takes humans around 20 minutes and 24,000 actions. So that's a lot. And just to let you know, here our agent is using a mouse and keyboard, just like a human would. So it's a very low level action space. We're not like building in macros to do anything. So if we do reinforcement learning with that reward scheme I just showed you, then basically nothing happens. That's the blue line here at the bottom. So no pre-training, you don't get anything. But if you've pre-trained on the internet, and then you start rewarding it for making progress in the tech tree, it slowly figures out over time how to do this extremely complicated set of actions that, again, 24,000 actions, skilled human, 20 minutes using a mouse and a keyboard. So this is super impressive. I want you to think about what you could do on your computer in 20 minutes. Now we have agents that we can train them to do that. So this is basically the father of Operator, which is OpenAI's current computer using agent that can book you a website. This was where we decided to prototype that idea. And that is why they felt confident going and building that as the successor to this VPT project. So I'm not going to show you this whole 20-minute video. I mean, this is sped up, but even sped up, it would take too long. But I just want you to show you the agent knows how to drag and drop icons, to use like a little user interface here, and it's very, very efficient at going through the game. So I'll skip ahead here a little bit. Here is mining down. It goes and it finds this resource. It knows how to go get a bunch of iron and do really complicated stuff that I don't even know how to do in Minecraft, like place a furnace and place the iron and the wood in the right place and make this new resource and then get those tools crafted up and then race off to go get diamond stuff. So my AI is much better at Montezuma's Revenge and Minecraft than me. All right. A project I'm on currently at DeepMind is Sima. We took a similar idea. We're just training a generalist agent across 13 different video games. These are now like really fancy modern video games. And one of the most striking things is that if you train on 12 of these things, you transfer to the 13th one almost as well as if you had trained directly in the 13th one. That's the gap between the black line here and this blue histogram. So we're starting to see generalization in embodied agents with massive training, pre-training in these sorts of environments, which is encouraging. In fact, earlier when I showed you this Genie video, what I didn't tell you is that this is the Sima agent just dropped off the shelf in Genie. So you're starting to see this dream. Pre-training produces an agent that knows out of the box how to go act and explore in different environments. And so now we're basically having something that we could have a much more sample efficient open-ended algorithm. Okay, so to conclude this mini chapter of the talk, pre-training gives you a lot of skills that allows you to learn hard exploration tasks efficiently. That should greatly catalyze our open-ended algorithms where we could automatically generate environments. Okay, so in the rest of the talk, I'm going to show you very quickly a couple more papers that I've been working on lately, where we basically apply this playbook. We're going to do an open-ended algorithm plus a foundation model somewhere in there and Omni. And so the first one I want to tell you about is the automated design of agentic systems. It was done with Shenren and Tong, excellent scholars. And the idea here is that, as you probably know, LLMs used to be a thing that you gave them a prompt and they gave you an answer. But increasingly, an LLM is kind of like the core engine in this more complicated workflow. It might do a web search and then get the results and put it in prompt. It might do a web search and then summarize the results and put the summary in prompt. It might have a debate amongst 4 copies of itself and then have a judge the debate, pick who the winner, and then return that answer. There's all sorts of complicated stuff you can do with an agentic system. You can do chain of thought, you can do reflection, etc. So as you look around the world, you see all these complicated agentic systems. That's what we're calling once you have a foundation model within one of these complicated workflows. And these agentic systems are being designed by hand and they're getting very complicated. Well, according to the AI generating algorithm philosophy, that's not what you want. Why manually create it? Why not use machine learning and AI to search for better and better agentic systems? So we're going to do that with ADAS, and we are going to use open-ended principles. So we're going to grow an archive of interestingly different, high quality, different agentic systems to search for one that ultimately is very good. So we have this thing we call meta agent search. We're going to define a search space for agentic systems in code. So we're going to search for them in Python, which was a first. And this is Turing complete. It can specify, because Python is Turing complete, it can specify any agentic system. And we're going to create this open-endedness loop. We're going to have this archive of the current stepping stones, the current agentic systems we've discovered so far. Take one out, ask a foundation model to improve it, make a better one. And then we're going to use Omni to say, hey, does this new one count as interestingly different versus everything that we've seen before? And if so, then we're going to add it to the archive. We'll evaluate it, see how its performance is, add it to the archive, and keep going. So specifically, we will say, hey, I have a new agentic system I've just created. If it's the highest performing version of that type of agentic system, then we'll add it in, like map elites. But if it's interesting and weird, even if it's not that high performing, we'll also add it in. So we have this quality diversity kind of flavor going on. What you can see is that it starts out really low performing, but over time, the more compute you give it, the better it gets. And it surpasses all of these hand-designed state-of-the-art agentic systems that people have published to great fanfare in the community, searching for a better and better answer. If you go and you take the final best answer, you can see it here. It did all sorts of really cool and interesting stuff, including at some point, I think it creates like an ensemble of different experts. And then it kind of judges which of these experts produce the best answer and goes with that. So we applied it to a lot of different domains like math and science, and it performed way better than many of these other state-of-the-art systems. We also, once you take one of these agentic systems that you made for math, you can generally take it and apply it to an entirely new math domain, and it does really well. So these generalize, they're not overfit to whatever they're doing. You can even take an agentic system that was designed on math, transfer it to a non-math domain, and it still does really well because the properties of a good thinking system are quite general and they can apply to many different domains. So our follow-up project to this, we thought, what do we want to do next? And the answer was, hey, ADAS was spitting out better agentic systems, but the thing that was creating them was not changing. What if we allow ADAS to modify itself? So it gets better and better at improving itself, and then better at improving itself, et cetera, forever. So we call that the Darwin Gödel Machine. The reason is because Schmidhuber in the early 2000s created this idea of a Gödel machine. This is an AI that it searches through its code and it says, if I can create a new code diff that is theoretically proven to be an improvement over my current self, then swap it in. And this was a theoretical idea that hasn't really been realized in practice, and that's because it's basically impossible. You're never going to prove in any complicated domain that a thing is definitely better, QED. So instead, we're going to look for empirical results. We're going to say, grow an open-ended archive of different agentic systems, test them empirically like on a software engineering task. If you are better on that task, there's pretty good evidence that this is an improvement or it's interestingly different, we'll add it in. And so we do that. That's the Darwin Gödel machine. It has the same basic open-ended loop, growing an archive of interestingly different stepping stones. We have periodically evaluated on the software coding benchmark, because if you're better at coding, you're probably also better at coding yourself. And here's yet another phylogenetic tree. So these are becoming routine and they're beautiful to see. And so you see all this diverse exploration. Some things are low performing, some things are higher performing. And ultimately we get this star creature down here, which was the best thing we ever saw. On the right, we show you its performance over time. And what you'll see is that on average, that's the blue dots, the performance goes, so the performance of the best agent over time kind of goes up. We increasingly find better stuff. On average, performance is also going up. But what's really cool is the black line here is the lineage to the best final agent. And what you'll see is it went through local optima. It got worse before it got better twice. So if you were being greedy, if you weren't doing open-ended search, you never would have found this agent. You had to allow some stuff that was weird and not high performing, because that ultimately might be the stepping stone that leads you to the big breakthrough. Also cool is you can do science to say how important are the principles that you are selling me. So one, blue here is the Darwin Gödel machine. Green is if you don't let it improve itself. So one thing is just producing stuff in an open-ended way, kind of like ADAS, but it's not improving itself. So that doesn't work as well. And if you take out the open-ended property, you don't have an archive of weird, different, interestingly high quality stepping stones, but you just do like a hill climbing agent that's always going to try to get better, you get orange or yellow, whatever that is. So it really doesn't work. So the principles of open-endedness are key, and the principles of self-improvement are key on two different domains here, which is the left plot and the right plot. All right, so I do want to mention safety. I worry a lot about AI safety and existential risk. To do open-endedness research, self-improvement research, you have to really prioritize safety and make it safe. So we follow all of the best practices in the community and we invent our own. We containerize these things, we monitor them by hand. We try to make sure that this work is going safe. But I do think we need much more work. Like we need to create something like a constitutional AI that says to the system, while you are inventing and exploring interestingly different stuff, don't do it if it's, don't explore a certain direction if it's not safe. Like don't explore how to create, computer code that can hack the NSA or, a bank or something. And so we've written a bunch of opinion pieces. I have one in Science with Jeff Hinton and Sheila and Daniel Kahneman and Yashua Bengio. And we have this one in particular at the bottom here, which is specifically about open-ended and self-improving AI and how you balance exploration with safety. So I encourage you to check that out if you want. All right, so to conclude this part of the talk, I think it's much better to go from handcrafted to learned agents. That's definitely where the future is pointing. These things can self-improve. They will get better over time. And the more compute you add, the better. And all of this kind of falls out of the AI generating algorithms philosophy. And the principles of open-endedness are essential to make that search work really well. Okay, I think I have two more mini papers and then I'll conclude. So the next thing I want to point out is this work that we had called the AI Scientist. So here we're really going to try to push towards fully automated, open-ended scientific discovery. It was done with these wonderful co-authors here. So science is the ultimate open-ended domain in many ways. And, as I mentioned, an example of open-endedness is the human community of scientists in like discovering new stuff forever. So can AI automate that entire process? That's what we pushed on in this paper. And I think we've shown that, yes, that is now within the realm of possibility. So our domain here is the science of machine learning itself. That's because in machine learning, the computer is the real world. There is no like simulator of a vial of liquid. If you get a machine learning algorithm to work better in a computer, you're done. But this same idea, the same algorithm could be applied to other domains if you have a simulator or an automated lab, like a chemical lab. So the AI scientist, to cut to the chase, this is a system that generates its own research ideas. It designs and runs its own experiments to test those hypotheses. It then analyzes and visualizes its own results. It writes the entire scientific manuscript from the first word of the title to the last period in the reference section. And it conducts its own peer review. So on the right here, you can see a thumbnail of a paper that it wrote. In the future, we haven't done this yet, but you could then apply the open-endedness principles. You could have an archive of papers that are interesting and different, and you grow this archive of discoveries, and then the system reads its own discoveries, publishes the next paper, and the next paper, and the next paper, and you basically have a simulated machine learning community in a data center. So we created an automated reviewer for this system, and we found that it's about as good as humans in terms of being reliable. Like humans agree with humans about as much as our AI reviewer agrees with humans. And that allowed us to automatically judge which papers were good enough to be sent to humans for review. Here is that thumbnail of the paper I showed you. And in general, according to our automated reviewer, our papers are getting about a 3 to a 6, maybe a 2 to a 6 on like the NeurIPS or iClear Classic scores. And a 5 to a 6 sometimes gets accepted at conferences. So we're kind of within realm of something that might get accepted, at least to a workshop. And so one interesting thing that happened is that we had a paper internally, an idea that was generated by the AI system, an entire paper. And I read this idea and I was like, you know what? This is actually a pretty good idea. Like if my grad student came to me and proposed this idea, I would say, yeah, that's totally worth doing. You should go do that. So I moved on, and then like 3 weeks later, a team on Twitter announced a paper that was the exact same idea. So independently, a team of humans had the same idea as the AI scientist. They executed it better, but it was really well received by the community. So it shows you, many people dismiss LLMs as not being creative and not being able to come up with cool ideas. I think they're wrong, and I think that history will prove them wrong, and I think we have one example of that right there. All right, we then created a V2 of the AI scientist. We did some minor technical stuff, but the main thing we did is we wanted to see, can this thing actually survive peer review? So it generated about 30 papers. We took the top 3 by manually reading them all and saying, these are the 3 we want to submit, because we didn't want to overload the peer review system, but we could have just submitted all 30. The final 3 that we did submit had no human touch, except for just that we chose them amongst the set of 30. We submitted them to iClear with the permission of the organizers, and one of the papers was accepted at an iClear workshop, and it was in the 55th percentile. So it did better than 55% of human-authored scientific papers. So, we're getting close to human-level AI research. This is currently in review at Nature, so wish us luck. All right, again, we did this with containerization. We fully watermark every paper, full transparency. We always tell everybody if a paper is AI generated, with one exception, which is the reviewers. That would bias them. So we told them there was a chance that a paper they would read would be AI generated, but not which paper was AI generated. But more work is needed. We don't want these systems to explore dangerous types of science, like gain of function research in viruses, for example. And we don't want them to do unethical science. So we need ethical AI scientists, and that's an open area for future work. We also have to think as a community about, are we going to allow AI-generated science to be judged on its own merits at conferences, or do we want a human game that we're playing that's different from the AI game? That's a community discussion to be had. So to conclude, we're now at the beginning of the time when the entire process of science can be automated. I used to see this joke all the time when I was in grad school and a postdoc. We'd do something that was a little bit automated, and when somebody would say now we just need the AI to write the paper, and everyone would be like, ha ha ha. And I always kind of thought actually I think that's possible. We just need a little more better algorithms, and now we have them. So I just want you to remember, this is the worst it will ever be. You're probably sitting here, maybe you've looked at the paper, you're not impressed, but look at the faces of AI generated images from 2014 to 2024. Apply this to Genie, apply it to Omni, apply it to the AI scientist. All of this stuff is getting better fast. So for future work here, we can scale it up, different domains, better models. But the main thing I'm interested in is the open-endedness thing. Can we basically simulate a community of scientists that build on their own discoveries? I think that's when you're going to see truly novel, massive breakthroughs produced by AI that humans did not in any way come close to inventing on their own. Everything here is open source. Okay, the last thing I want to tell you about before I conclude is I want to harness open-endedness for safety. The idea here is, can we leverage the power of open-ended algorithms to improve AI safety specifically? So this was also done with Song and Senren. This is automated capability discovery, or ACD. The idea here is that before a new model, you train a new model like GPT-6. Before it's deployed, you probably want to know, does it have surprising new capabilities that are dangerous? Does it have surprising new failure modes that are embarrassing or are also dangerous? This is a very difficult problem because, these systems are general. They can do you can ask them about almost anything. So how are you going to cover the space of all possible things they could do? Well, you're not, but you could try to do something automated. Currently, we mostly figure out their surprising capabilities and failure modes via crowdsourced investigation. We release them and then the community figures it out. But unfortunately, bad things can happen while the community is figuring that out. So we want to see, can we automate this? So we're going to take a subject model. This is the new model we want to learn about. And we're also going to create a scientist model. This is another foundation model that's going to launch an open-ended algorithm that tries to search for interestingly different capabilities and failure modes of the model, and then it can keep exploring and riffing based on what it's discovered so far. So we can do that automatically. It ends up kind of finding clusters of things that the model is really good at or really bad at. It's automatically generating the question. It's automatically judging if the answer is right or wrong. It's automatically judging whether that is a surprising result or not. And you just repeat that process forever. It ultimately writes a full report that you can then read and be like, okay, I should or should not release this model. Now, it's not perfect. You can't assume that just because it didn't find something, there's not something out there. But it gives you a good kind of a snapshot, a good initial feeling for how your model is doing. And it might uncover some stuff that your red team might not uncover. Okay, so I mentioned that this playbook is very general and powerful. I've told you 4 papers so far that use it: ADAS, the DGM, the AI Scientist, and ACD. I don't have time to tell you about these 2 in green. You can check them out if you want. We have papers on them. But basically, the sky's the limit in terms of what you can do with this playbook. So 3 concluding slides, and then we get to have fun with Q&A. So quality diversity algorithms, I introduced them. They explore really well. They create and collect what we call stepping stones that are like things that we've invented that can lead to new discoveries, like an agent or an environment or an idea. They harness goal switching, and they invent these effective counterintuitive curricula. I've also introduced open-ended algorithms where the goal is to truly endlessly learn and innovate forever. Like evolution and human culture. I think this is one of the grand challenges of all of computer science. I think there's a Turing Award waiting for whoever cracks this. I've also introduced AI generating algorithms, which is basically an open-ended algorithm specifically kind of focusing on trying to make ever smarter systems, better AI. I think that's the fastest path to producing real powerful AGI or ASI, and therefore is both worthy of a lot of focus, but also has a lot of safety implications that we need to be very, very, very serious about. I introduced Omni so we can finally pursue what's interesting and avoid all the pathologies where we tried to define that manually before. The concept of Darwin complete search spaces, where you have basically the most vast environment search space possible. You can either do that with Omni Epic and use code to generate the environments, or you could do it with Genie and have a foundation world model be your environment. We talked about how you can pre-train agents like with VPT and SIMA. That allows you to have a sample efficient agent that seeds the process. So it's like it starts with something that's pretty smart, and you can skip to real learning and the open-ended learning process in a more efficient way. One way to think about this is that evolution took 3.5 billion years to produce you, and then look at what you have done in 100,000 years or 200,000 years. So by pre-training, we can kind of skip and leapfrog to the interesting part of open-endedness and get past the flatworm part. Finally, open-endedness and AI generating algorithms plus foundation models plus Omni is just a really general and powerful playbook. We saw the automatic design of agentic systems, the Darwin Gödel Machine, the AI Scientist, intelligent trial and error, ACD, et cetera, et cetera. All of these things are basically just taking the same playbook and applying it in different ways, and it all works really, really well. So I'm going to leave you with these 2 thoughts. One, open-endedness and AI-generated algorithms, I think, are the next big wave in AI. So I would encourage you to think about this. Like, what could you do in your world with this set of ideas? Thank you very much.
Thanks, Jeff. I'm exhausted. So we're now transitioning to the, that was a great talk, and a lot in there and a lot to unpack. So thank you very much. It was really inspirational. We're now moving to the question and answer period of our seminar. And so for everybody in the audience, please use the raise hands function or the chat function. If you feel comfortable doing so, we'd really appreciate if you turn on your camera when you're asking a question. So if you do raise your hands, our team will send you a request for you to unmute when it's your turn to speak. So thanks. And it looks like Brian Harrington, who looks like a collective. Brian, the floor is yours.
All right, running it. Hi, Jeff. There we are. Hi, can you hear me?
I can, and I can see you.
Wonderful. Yes, we thought we would. We're here at UTSC showing a group of people watching you. So your numbers are, I guess, deflated if you look at just the number of people here. So we've been sort of having a bit of back channel chat about this. One of the things, fantastic work, by the way. One of the things I really was thinking about all the way through is that AGI almost seems to become a pruning problem at a certain point. If you had infinite resources, infinite depth, infinite breadth, those phylogenetic trees would almost all the way along have eventually solved the problem, but you don't have that. So at some point you're pruning. And so you describe sort of Darwinian evolution is kind of a pruning process. And Darwinian evolution has sort of two levels of pruning. One is systematic, right? Some other creature comes in and outcompetes you for your resource, which seems to be a lot of what you've been modeling. The other thing, though, I find is there's a lot of stochastic pruning, right? Dinosaurs were a better fit in almost every niche, and then meteor comes along, and that gets a whole new generation, which seems to sort of boost. So I'm just wondering your thoughts on that, like how much stochastic process should you put in there to sort of say, yeah, we're getting the best now, but let's, throw some randomness into it to see if we can get out of more local maxima.
Thank you for the question and for showing me the room. Yeah, there's a lot of fun things to think about. So I'll just give you some thoughts that I have. One is that Andrej Karpathy actually mentioned this a long time ago in one of his talks. He's like, we know how to solve AGI. It's simple. You just randomly generate the weights for a neural net and you repeat forever. Eventually, theoretically, one of them will be AGI, right? And so putting aside architecture search, that's true. But the space of possible neural net weights is so unimaginably vast that you could never do that in the universe that we have. So the way he put it is, how do we do that without burning forests? But it's even worse than that. I mean, we don't have enough molecules in the universe to there's more neural nets than there are molecules in the universe, so it's never going to work practically, but theoretically true. But yeah, it is in some sense, all search is in some sense pruning, because you could just exhaustively search it and the answer is in there somewhere. But once the search space is so unimaginably vast, it's kind of like a theoretical point only. It's just not practical. Another thing which is I want to point out is that you're right about pruning. It also applies to evolution. So I think it was my advisor, my PhD advisor, who's a philosopher in grad school. He wrote a book in which he likened evolution to topiary. Topiary is when you grow a bush and then you trim it down to make it look like a poodle or like a spiral shape or whatever. I mean, evolution, if nothing ever died, if everything got to reproduce, it would be like a bush that grows forever in all directions. But then it's selection and some comets and things like that prune off bits, and then you end up with something that doesn't look at all like something where everything got to grow. It's very shaped by selection. And so, yes, the job of search, of intelligent, healthy, useful search, is to say brute force is not going to work. Exhaustive search can't work. And so we have to intelligently prune and focus on the good and promising directions, but not prune so much that we get trapped in local optima and we hit these dead ends and our search stops to explore and be good. And so in this talk, I've kind of focused on what I think is the best set of ingredients to do that well. Specifically to your point on stochasticity, one thing you can do is if you are putting all your eggs in one basket, like dinosaurs. You can hit them with comets every once in a while to knock them off their pedestal and hope that the next all your eggs in one basket thing goes somewhere else, doesn't get trapped in the same local optima and goes somewhere good. But I think even better is to kind of just simultaneously go in many good directions. And if any of them hit dead ends, you don't even need the stochasticity. I think you can just go around and find the other good stuff. But stochasticity can help for sure. It can like basically help you with little like minor local optima, like nudge you out of stuff. But I think that if you just do like hill climbing with stochasticity, you're never going to solve hard search problems. I really think you need this kind of quality diversity, open-ended exploration, because it's just much more principled. It's a much more principled way to explore than random search. Another example, look at exploration and reinforcement learning. Randomly stochastically mashing buttons doesn't solve Montezuma's revenge. You need something that's more principled, like a quality diversity algorithm or Go Explore to go and handle that. So I don't know. I hope some of those answers hit the dartboard that you set up for me.
Thanks, Jeff. I think we're going to move on to the next person. So Francis Kong Wang, you are the next person with your hand up.
Hello, hi, can you hear me?
Mm-hmm.
Okay, thank you,
I
Jeff,
can
for
see
the
you. Nice library.
yeah, thanks, Jeff, for the presentation. I do some research into strategic foresight for sustainable innovation in Canada, and then this gave me idea about using AI to do this kind of exploratory research in what innovation can be generate or cultivate. I did have a question I want to ask. I want to preface that saying I'm a big fan and supporter of safety guardrails in AI. But I want to ask this way, just kind of to explore this idea being, because when I saw Omni being notions of interestingness and using a foundational model, there's also human notions of ethics, right?
Mm-hmm.
And I want to ask about this, some of the graphics showed us about the model's evolution being hitting this local minimas. I want to ask, just on the concept of open-ended exploration, what if these some unethical agents and behaviors are actually the local minimas to explore into higher, more ethical final outputs? Because then I'm just saying the question because this happens with our real, actual human history. Great sufferings leading to technical advances, times of conflicts of work create a lot of technologies. Human death and suffering is thrown into pyramids to inspire different actions, right? So just wanted to toss it out there and then using a foundational model to guide notions of interestingness or notions of ethics, what are the implications there? I don't have an answer for this. I just really want to have this discourse with you.
Thank you. I think that's one of the most interesting questions I've ever been asked in my career. So thank you for that. It's a tough one, right? You're basically pitting my principles against each other. And I think that my answer is, or at least not, I don't think I know. My answer is, even if creating unethical agents was an important stepping stone to get to really powerful AI, I would not want to do that. Like, that is not worth it for me. I'm too worried about AI safety and existential risk to want to create like AI Hitler to unlock something that is better and more virtuous. Because what happens if that thing figures out how to get out of the box, like right there? Or what if that thing does some really unethical research, like the horrible stuff the Nazis did with twins? Or it creates some gain of function thing with COVID. Like, it's just, we're playing with fire there. And I'm not so motivated to accelerate AI at all costs that I want to play with that fire. I think I'd be happy to not do that. The one exception I could imagine is if we felt extremely confident in our sandboxing and it was in like air gapped and we thought there was no way out and it's not interacting with humans and it's not even like a full AGI that could like do any real mischief. It was just doing something really like narrow and scoped. Maybe I'd be like okay to play with it as long as the unethical stuff it was doing was all simulated. Like, it can't actually do it on real people or it can't create a real virus. Like, I could imagine some version of that where it would be interesting to test your theory. But my default instinct is like, I don't think we need it. And so like, let's not even go there. Let's just do it in another way.
I like that answer. Okay, Caleb. The pressure. So our next speaker, our next question is from Caleb Bidult. Bidulp. Sorry, you can correct me on the pronunciation of your name. So please go ahead.
Yeah, so really great talk, and I'm glad to hear that you're concerned about X risk and making AI generating algorithms safer. So I'm actually working on a project to show how this sort of like ADAS kind of system might be inherently safer and more interpretable than typical RL. So like the nice thing about systems like ADAS is that if you keep the foundation model fixed and just optimize the code and prompts, you can just read off all the strategies it learned. So I think your work focuses more on like general strategies that are useful everywhere, like ensembling or like self-critique or a better coding interface in the case of DGM. Um, but in theory, you could learn like more specific strategies where the prompt explains how do you get reward on like particular tasks. So for instance, like if you're counting on letters in a word, then you should break it up with spaces. Some strategies would be reward hacks, like lie to the user and make fake citations. But this would actually be really great because then you can just like see that reward hacking strategy in the prompt. It's like really obvious. And so yeah, what do you think would be the main obstacles to being able to express maybe like all strategies or as many strategies as possible just via code and prompts? Like, to what extent does this kind of have to be implicitly learned into the weights? I guess like one particular uh, problem you might run into is that the code would get really, really complex and unwieldy if you try to write down all of your strategies for like every single kind of task.
Yeah, great question. So I didn't want to exhaust Sheila too much. So 2 papers I left out touch on that. So we have one paper called Thought Cloning, which I encourage you to check out if you haven't heard about it. So the idea here is that you train an agent via behavioral cloning. That's the default thing that we do a lot. So you make an agent take the actions that a skilled human or a skilled agent takes, and it basically distills what action should I take in what situation. So thought cloning was the idea, hey, let's have a human solve tasks, taking a bunch of actions, like in Minecraft or whatever. But while the human is doing that, it's thinking out loud about what it's doing and why it's doing it, like what its high-level plan is, its low-level plan. Oh, this didn't work, so I'm going to replan. It's explaining all of its thinking. And you clone the thinking and the behaviors into an agent. That's thought cloning. And then in the end, you have this hierarchical setup where an agent has like its high-level thought producing module. It's thinking out loud, it's reasoning. We now call this reasoning. This came out before reasoning was a thing. It's doing reasoning, and then it's got this like low-level muscle memory thing that's kind of conditioned on the high-level thoughts, like, oh, open the door. It goes in and like knows how to like do the muscle commands to open the door. The benefit of thought cloning type systems is you get to watch them think out loud. And so one of the main things we put in the thought cloning paper is that this is really huge for AI safety because you're training an agent that's thinking out loud in interpretable English. And therefore you get to watch it. And if it says, hey, I'm about to I was just instructed to drive this passenger as fast as possible to the airport. And you see its thought be like, I'm just going to blow this red light, even though kids are crossing the street because I got to get there on time. You're like, stop it. You have like this way to intervene because you know what it's planning on doing and why. And like you said, you can see its strategies and its actions, and it's all interpretable. So I fully agree that agents that plan and reason and think in human interpretable language is huge. And one way you can get those agents is by training them on human data of thinking. So another thing I'll say is we recently had a paper called Foundation Model Self-Play. I had it as one of the things that I didn't have time to talk about. And here we have 2 different populations of agents that are competing in some sort of a game like Dota or StarCraft or Minecraft. And they're trying to kick off a coevolutionary arms race, a self-play system, and get better and better. But the AI is basically creating it's creating strategies in code. And those are interpretable and you can read them, and then you can basically see what's happening as it happens, and it's all very interpretable and cool. So I think this is promising, but I think you pointed out one of the biggest problems. Well, one of 2. One is code gets very, very, very complicated. Like we all know that you can't review like all of Enron's code quickly and figure out what they're doing. And so if these systems are spitting out code massively in some big self-play learning algorithm, it's hard for humans to keep up. You can use AI to help with that, so there's tools you could use. The second thing is you still have a foundation model in there, often in many places, and that thing might be a black box. And so nothing's perfect, but it's way better than the alternative, which is just like have these black box systems. So I think it's all very promising. It's one of the best ideas we have for AI safety is like make them love us and make them think out loud. These are kind of the 2 best ideas I know of in AI safety. So I'm fully supportive of this kind of work.
Great, thanks. So we have about 7 minutes left. There are two people who have their hands raised, and I have like about 30 seconds of closing remarks. So I'll encourage everybody to be as concise as possible, both in their questions and their answers. And next up is Evie Mika. Evie?
Hi everyone, thank you Jeff for the amazing talk. So my question is also about AI safety and how we will not lose control of these all self-improvement algorithms and AI generative algorithms. And so my question here is, there is any systematic way to really keep people, humans in the loop, so we don't lose control and we don't just intervene whenever it's necessary, but in each step somehow people are aware of what's happening and we get their feedback, and essentially as we do all this search, we don't just to see some self-improvement without really getting the feedback of the human systematically. And also something that is kind of related is that in your talk, you mentioned about how we learn interesting new environments. And so I'm wondering if you have any definition about what is interesting, and whether when we have a particular definition of what is reasonable to explore because we gain new knowledge, whether this is something that we can communicate to an AI algorithm, and so in a rigorous way they can find a new state that is interesting, they can learn there without really doing all the search, and also stay in the safe place as much as possible.
Okay, I'm going to answer the first question first. I think that I don't want to close down avenues. As you can imagine, I like open-ended search, right? So I don't want to say like, here are the one or two things that I think we should do for safety. I would just encourage this to be like a very important research area for the whole community. We need a lot of the best minds thinking about how to make these systems safe, including specifically self-improving systems. Because like, I just don't kid yourself, the world will not try. Like people are going, even if I shut down my whole research program, somebody else is going to try to make self-improving AI. So what I have concluded, since I'm not king of the world and can't pause research, is that it's going to happen. So we need to try to make it safe. And so I encourage people to try to research this subject, to try to figure out the best ways to make it safe. I don't know the answers. Some ideas I have, one thing I think is probably almost certainly likely is we need an external monitoring AI. You could try humans if you want, but human resource is very limited. But a bunch of AIs that are watching the system and are flagging if anything is dangerous or worrisome, flagging it for human review, and pausing the system and asking the human to come check. And those AIs are not being optimized according to the same objective functions of the overall system. They don't care if the system is improving. They don't care if it's interesting and weird and new. Their job is only safety and to let us know if something weird is happening. And since they're not being optimized, they're much less likely to be exploited. However, the system might learn to trick them, and so that's part of the real challenge there. So how do we prevent that from happening? And I don't have all the answers there. That is, I think, one really important ingredient. I think another one is the system has to have those values baked into it, that it just doesn't want to try to trick us. It doesn't want to try to trick the judges. It doesn't care so much about whatever goals we're giving it that it's willing to do unethical stuff. Now, how do you create a system that doesn't just ditch that because it wants to go optimize for these other objectives? I don't know. I'm aware of Sheila wanting me to go fast. I didn't fully catch the second question. I just want to say that I think that one thing that's really interesting is like, as the system innovates forever and gets out of distribution, how does the system continue to judge what counts as interestingly new as it gets far away from like its training data? My personal thoughts on this, if that's what you were asking, is that I think it's not as hard because you're always conditioned on the archive. You don't have to know if an iPhone is interesting. You just have to know if an iPhone is interesting given everything that came right before the iPhone. And whatever happens in 100 years, you don't have to know if that's interesting now. You just have to know if that's interesting conditioned on whatever came in the couple of years right before it. And that's a simpler problem than objectively knowing everything that's interesting. Thank you.
Thanks, Jeff, and thanks, Evie, for the question. So our last question goes to Daniel Khorasanian, and we technically have about 3 minutes, but take the time you need to honor the question.
Yeah, thank you very much for the talk. I'm Daniel. So my question is about the metric used for the evolution of the environments in open-ended models. So I mean, if it's increasing the complexity or just being different from previous one, an application that come to my mind is like when we want to solve a complex problem, we gradually make it simpler until we observe some patterns, and then we go back to the original problem. I'm wondering if this kind of models are used to the complex problems or not?
Yeah, so we definitely have that in our system. So Omni, it looks at the current set of tasks that the agent has tried to solve in the past. And it looks at its performance and its learning progress. And it says, hey, I've been challenging you on these things here, and you're not learning at all. And then the language model has to decide, is that because it was impossible and I'll just move on to totally different class of problems? Or was it just too hard for you right now? And it can come up with a simpler version of the problem and see if you make progress on that. It can make it even simpler. If that doesn't work, it could walk it all the way back until you learn that. And then it could then go back and retry these different things. And just like a human teacher has to kind of use its intelligence to figure out, when should I abandon a class of problems? When should I simplify them? And when should I revisit the harder ones that earlier we weren't seeing learning on? It's kind of up to like the foundation model in Omni to like try to do that the best that it can. And so it can do all that stuff. To the extent that it does it really well versus not, that's like an empirical question. We need more scientists to go look at that and make those things better.
Very interesting. Thank you very much.
You're welcome.
1 minute to spare. Excellent. So Jeff, first and foremost, thank you to you. Thanks for such a stimulating talk, for sharing all this great work that you've done. And I think the audience as well really appreciated the focus on AI safety as well, and the insights that you shared with us. I also want to thank our audience for some great questions. Sorry to Bill and some of the other people who weren't able to have their questions answered. But hopefully there'll be another opportunity or another speaker with whom you can engage. So this concludes our seminar, and a big thanks to Jeff. And to those of you who are in the audience, and to Jeff as well, please join us next week on Wednesday, September 24th, as we welcome Hamza Bastani, who's an associate professor at the University of Pennsylvania Wharton School, for a talk entitled Unpacking the Unintended Consequences of AI in Education. And for details and to register, just visit the SRI website or click the link in the chat. So thank you very much, everybody, and enjoy the rest of your day.